as we discussed bases, I often had to make the caveat that we were working with a finite basis. And that's because vector spaces where you can write a finite basis and vector spaces where your basis has to be infinite actually behave kind of differently. And what we're going to be working with mostly for the rest of the class will be vector spaces where we can write a finite basis. So we aren't going to have too much to say about vector spaces with infinite bases. Just to give you a flavor for why these can be kind of difficult, there are three examples. One is, let's look at the vector space of all polynomials. Okay, so the vector space of all polynomials actually has a basis that's pretty easy to write down. You can just take 1, x, x squared, and so on. You can see that this basis isn't finite. There are infinitely many positive integer powers of x that you need to get all of the polynomials. So we do have an infinite basis, but it is a basis that's pretty easy to write down, right? There's no linear dependence relationship among the powers of the positive integer, powers of non-negative integer powers of x. And these all span the space of all polynomials because any one polynomial is a sum of, right? So any polynomial can be written as some linear combination of these powers of x up to power n for some maximum power of n. So this is possible when our polynomial has degree n, right? So, some vector spaces with infinite bases kind of act nice, but other vector spaces with infinite bases sometimes don't. So, as an example, let's let S be the set of all sequences of real numbers. And by sequences, I mean infinite sequences. So that is to say, lists of real numbers that go on forever. Okay, this has adding these term by term and doing multiplication term by term gives you a vector addition and scalar multiplication for these. So what would a basis for this even look like? Well, I mean, you'd think that this would give us a basis. So for one basis element, just take the sequence that has a 1 in the first spot and then zeros everywhere else, and then a 1 in the second spot and zeros everywhere else, and so on, right? 1 in the third spot and zeros everywhere else. You can see this looks kind of like the standard basis for Rn, except each element is, or each vector is a sequence instead of just an infinite sequence instead of a list of finitely many things. And also there are infinitely many vectors in this list. Well, these definitely are linearly independent, right? Because just because of where the non-zero elements are, there can't be a non-trivial linear dependence relationship among these things. But if you ask yourself, do these span S? The answer is no, which is a bit surprising. You might think, well, look, if we have a sequence S0, S1, S2, an infinite sequence of real numbers, isn't this the same as, so if we call this one E1 and this one E2 and this one E3 and so on, isn't this the same as S0 E1 plus S1 S0 E0, I guess, I have my entries offset by 1, which is a little inconvenient, so why don't I call this S1 and this S2 and this S3. The computer scientist in me that wanted to start with index 0 loses out this time. So it seems like this should be, well, isn't this equal to S1 E1 plus S2 E2 plus, S3 E3 and so on out to infinity? Well, yes, but this is not a linear combination. If you look back to when we defined a linear combination, linear combinations have to be finite sums. And this is an infinite sum. So these are equal, but this isn't a linear combination. So is there any way by taking finite sums of producing this sequence from these elements? And the answer is no, right? Any finite combination of these elements will have a last non-zero entry, and this sequence might have non-zero entries beyond that. So in general, it's impossible to get every sequence as a linear combination of finitely many of these elements. So even though it looks like this is a basis, actually it's not, right? The span of these elements is a vector space that is smaller than S. So what does a basis for this vector space even look like? It's a little hard to say. So, this is just one of the many complications that can crop up in vector spaces where you have to deal with infinite bases. Sometimes the bases are much more complicated than you might think. And so for that reason, most of the time, we will be working with vector spaces that have bases that are finite.